Hello everyone. So today my team is going to present about our machine learning project, which is on cross-domain plant species identification. So our team members consist of the team leader Darren, Esther, Jane, me, Legend Hall, and William. So this is our presentation outline. So to start off, we have our introduction. So deep learning has achieved strong performance in plant species identification. However, many plant species, especially tropical ones, lack sufficient field photos, making training difficult. So Herbarium images, which are the pressed dry specimens, are far more available and well created. Recent research explores using Herbarium images to help identify species in real-world field photos, forming a cross-domain identification task. So the problem is simple. The field images and Herbarium images actually have quite different features. So models trained on Herbarium images alone often fail to generalize to field images, and data-deficient species also makes the challenge harder because there are few or no field samples for certain classes. The task is to build a model that learns correspondence between both domains so it can correctly identify species in field images even with limited field training data. So let's start with setup and pre-processing. So first, we're going to import the necessary libraries and dependencies. So in this case, we're using PyTorch, and we're going to load the data and along with its annotations and create global class mapping between them. And we're going to split the data into training and validation and perform normal, simple data augmentation to it. So the first approach is going to be the mixed stream CNN. So I'm using the convnext best model we train on ImageNet, and the strategy I'm using is partial fine-tuning, which includes freezing the early layers to retain generic image features and fine-tuning the later layers plus the classification head. And these are my configuration and settings for the training. So from the three graphs above, you could observe that the model achieved a stable convergence around epoch 10, but you could also see a quite severe overfitting to the training data. So this is probably because of the lack of dataset for each classes. As for the table below, you could observe that the model actually did quite well for the images with pairs, which achieved an top one accuracy of 86.93. However, it achieved a quite bad accuracy for without pairs, which is 12.96. So this further proves our point that off-the-shelf models today do not perform cross-domain plant species identification.
For baseline 2, we shifted from CNNs to a foundation model approach. We used Dino V2 with B/14 as a frozen feature extractor, followed by an SVM classifier. The motivation was that a transformer pre-trained on massive plant-relevant datasets may capture deeper semantics and potentially generalize better across herbarium and field images. First, both herbarium and field images go through resize, center crop, and normalize because widths are sensitive to spatial distortion. Next, the image passed through the frozen Dino V2 backbone, which outputs a 7680 dimensional embedding. We standardize these embeddings and fit them into an SVM with an RBF kernel where C and gamma are tuned to using a grid search. We train in two phases. Phase 1 is linear probing, which only the SVM learns, while transformer stays fully frozen. In phase 2, we add light fine-tuning, where we unfreeze the last transformer blocks with a very low learning rate. So, the model can adapt without overwriting its pre-trained plant knowledge, and both phases share the same transforms and batch settings. Performance reached about a 73% top 1 and an 82% top 5 overall. With paired species, accuracy jumps over 92%, showing Dino V2 as an excellent feature extractor when domains align. But for unseen species, accuracy dropped to around 16%, meaning the cross-domain gap still unsolved. So baseline 2 becomes our bridge. Strong pre-trained features but still limited generalization, highlighting the need for domain adaptation in our later models.
I'm Esther, and my approach focuses on synthetic data generation. To solve the cross-domain issue, I designed a two-stage pipeline. First, I use CART, an unpaired image-to-image translation model, to convert herbarium images into realistic field-style synthetic images. CART is trained using herbarium images as domain A and field images as domain B. So after training, the model generates synthetic field images for all unpaired classes. These synthetic samples are then added back into my training set to boost representation for those difficult classes. So I have a total of 6,488 training samples. For classification, I use a Dino V2 backbone pre-trained on plant data, followed by a linear heads with 100 species classes. To briefly explain my data transformation, the images are resized to 518 times 518 pixels, and random horizontal flipping is applied to training images only, followed by normalizing the images for both training and validation set. Training is done in two phases: head-only training, followed by full fine-tuning. Here are the final results after full fine-tuning. I achieved an overall top 1 accuracy of 72.95%, with class accuracy of 86.27%, and without class accuracy is 35.91%. So we observe a strong performance on paired classes, and even though unpaired classes remain challenging, the synthetic images successfully contribute to meaningful recognition improvement compared to using herbarium data only. So we believe that if time allows, this approach might be able to improve further by generating higher quality synthetic images by using diffusion model or by integrating domain adaptation techniques and prototype-based classification.
Thank you, Esther. So for my proposed solution, I developed a dual stream ensemble to solve the domain gap problem. Instead of relying on a single network, I run into two parallel. Top stream, the specialist, a hybrid model that outputs direct classifications. It excels at non-data-rich species. And the bottom stream is the generalist, a metric model that outputs embeddings. It is designed to handle rare data-deficient species. This stream fits into a dynamic decision gate. This module automatically decides which model to trust for each image, switching to the generalist only when the specialist is unreliable. To configure this, I utilize the Dino V2 backbone for both streams. I froze the initial layers and only fine-tune the last 5 transformers blocks, which allow the model to adapt our herbarium data without losing pre-trained knowledge. I also tune the specific decision gate threshold of 0.93 via the grid search. As shown in the table, the key difference lies in the loss function. A hybrid model uses a looser triplet margin of 0.3 mixed with cross entropy, while the metric model uses a stricter margin of 0.2, forcing tighter clustering to improve generalization on unseen classes. Finally, the results demonstrate why this ensemble is necessary. Looking at the top 1 accuracy on the left, the hybrid model failed significantly on unpaired classes, dropping to 22%, and the metric model was more stable on those rare classes. My ensemble successfully reached this gap, achieving an overall accuracy of 80.7%. The top 5 chart on the right further prove the model's robustness. When allowed 5 guesses, the ensemble achieved nearly 90% accuracy, confirming that even when the exact match isn't first, the correct species is almost always in the top candidates. So that's all for my approach.
Thank you, William. So you have seen our trials and errors. Our journey started with baseline 1 and 2. So while Dino V2 was slightly better than COS30082, both failed to generalize, scoring terribly on species without field photos. That led us to a bold idea. So why don't we create synthetic data sets if we don't have the field data sets? So we use FastCart to generate synthetic ones. Now, there was a breakthrough. Accuracy of those unseen classes jumped to 35%. Now, however, that came with a cost. The model got confused on the non-classes, so our overall performance didn't actually improve. Now, we even tried the famous DANT, domain adversarial approach with taxonomy mapping, but frankly speaking, the complexity didn't yield results. That is why we ultimately chose the dual stream ensemble. It was the only approach that gave us the best of both worlds. It is that better address the domain gap without heavily sacrificing the accuracy on the non-ones. So with the best model selected, let's see how it works on our GUI. Yeah, there we go. Due to some technical issues, I think the Group12 server is down. So at the time we have to locally deploy it, but it gets the job done. Thank you for listening.